Hello everyone, and welcome back. Today we're going to continue our exploration through multivariate statistics and focus a little bit on the basics of hypothesis testing in the multivariate world. Let's go over a few basics that we need to understand before we dive into the multivariate version of mean vector hypothesis testing. So, let's assume that x is a random vector with random variables x1, x2, all the way down to xk, and let's pretend that x follows a multivariate normal distribution. In particular, its probability density function is going to be of the form fx of x is going to be equal to 1 divided by 2 pi to the k over 2 times the square root of the determinant of the associated covariance matrix sigma times e to the power minus 1/2 x minus mu transpose times the inverse of the covariance matrix times x minus mu. Here x and mu are both vectors and sigma is a matrix, and we should of course recognize that term, circled in pink, as the squared Mahalanobis distance between the vectors x and mu, which can again be viewed as some sort of elliptical distance from the mean vector mu given here. Right, so what we're going to be aiming to do now is, because generally speaking we do not know the covariance matrix sigma, and we typically do not know the mean vector mu. So we typically have to approximate them in order to make any inferences about multivariate distributions. So as usual, just like the univariate case, we're going to be starting off with the mean. So let's actually do a quick review of univariate hypothesis testing for the population mean mu. So the null hypothesis is that mu is equal to some constant, and let's assume that we're going to be working under a two-tailed alternative hypothesis. And here we're going to be assuming that mu0 is just a number or a vector in R1. So a couple of the pieces that we need in order to understand this hypothesis test. First off is the unbiased estimator property of x bar, because we know the expected value of x bar is going to be equal to mu. And in case you do not remember what x bar is a random variable where x bar is defined to be equal to 1 over n times the sum of x1, x2 down to xn, where these xj's are just random responses, hopefully from the same population, and hence they have the same expected value, in particular mu. Also, one can prove via the variance properties, assuming that each of these observations are independent of one another, that the standard error associated to this particular estimate is going to be equal to the standard deviation of the population that we sampled from, divided by the square root of our sample size. But as usual, we usually do not know what sigma is, therefore we have to approximate the standard error with the standard deviation of our sample divided by the square root of m. Right? So if we happen to know the standard deviation of the population, then we can typically use a z-test statistic of the form our sample mean minus the claimed value of the population mean, all divided by the standard error of the estimate x bar, which is in disguise, if we sort of expand that expression out, is just sigma divided by the square root of m. But as usual, even though we know that this is going to be associated to a z distribution, hence we don't have to have any degrees of freedom, we usually do not know what this sigma is, and hence we have to estimate it. So we have to estimate this with x bar minus mu0, all divided by s divided by the square root of m. So we know that if these xj's are normal, this x bar is normal, this s will follow a chi-squared, and that quotient will follow a t(n minus 1) distribution. Right? So we usually call this a t-test statistic. Fair? So if that is the case, then we can also consider what we call a t-squared test statistic, which is just the square of a t-test statistic. And if we look at that formula in rearranged form, that's just going to be equal to n times x bar minus mu, the quantity squared, times 1 divided by s squared in expanded form. Now, we usually are perfectly fine with just working with the t-distribution, but this formula in t-squared world is actually going to provide a little bit of insight into some of the formulas that we're going to be talking about in the multivariate world. And also remember that the t-squared test statistic actually has some relevance when it comes to, for example, ANOVA test and multiple linear regression, because if we have, for example, the t-squared test statistic given to be, and we can rearrange that in the following form, n times x bar minus mu 0. And since it's a number, it's equal to its transpose, and then times 1 over s squared, and then times x bar minus mu 0. So this is just another way of writing that expression. This t squared test statistic actually will follow an f1 n minus 1 distribution, provided that that follows an n minus 1 degree of freedom. Okay? So also, before we move on to the multivariate world, keep in mind for k is equal to 1, i.e. one feature, our sample covariance matrix is the 1 by 1 matrix just containing our sample variance. So that means we can actually rewrite this t squared test statistic as t squared stat is equal to x bar minus mu 0 transpose times the inverse of the matrix sigma hat divided by m times x bar minus mu 0. And this representation actually gives motivation into how we're going to test this in the multivariate world. All right, so let's just briefly outline what we mean by the multivariate version of this test. All right, so now our focus is to extend this to multiple variables or multiple features, and hence we usually call it a multivariate approach. So the null hypothesis is that the mean vector mu1, mu2, down to mu k is equal to mu1, mu2, down to mu k, and the claims of each of them, right? And usually we will just abbreviate this by mu is equal to mu 0. Here, mu and mu 0 are both vectors now. So the first natural question that we need to ask is, how are we going to approximate a vector, mu, in particular mu1, mu2, down to mu k? Well, we already know point estimates for the individual components because we know that the expected value of x bar j is actually equal to mu j. So if we define a vector, say x bar, which is just x bar 1, x bar 2, down to x bar k, then we have the expected value of the sample mean vector x bar is actually equal to the population mean vector mu. So since we know a point estimate for this vector, we can use x bar as a point estimate for mu, just like we did in the univariate case. So now that we have some idea of what we're going to be testing today, let's lay out a few strategies that are commonly used and also discuss the pros and cons. So obviously we have some vector mu and we have another vector mu 0, let's say, where mu1, mu down to mu k are just a bunch of parameters that we don't know, but we can always make conjectures and propositions about their values. That's the mu 0s. So one way we can approach this, and let's just call this, say, strategy 1, is going to be element-wise comparisons. And what we're going to do is we're going to estimate them with classical confidence intervals. So what that means is we're going to take this null hypothesis and write it in sort of an element-wise fashion. So our null hypothesis will now turn into mu1 is equal to mu1 0, mu2 is equal to mu2 0, all the way down to mu k is equal to mu k 0. So instead of one vector, now we have k different hypothesis tests. So we know how to do these one at a time. So that's not a concern, therefore it's a fair strategy because we don't have to learn anything new. So let's assume that the alternative that we're working with is that mu j is not equal to mu j0 for all of them. That is a two-tailed test. A two-tailed test for each. And we're going to be choosing the appropriate test statistics like we did in the classical univariate case, so these will be definitely two-tailed tests. So if we approach this just like the old way, then we're going to have that the confidence interval for parameter mu j under some level of confidence c is going to be equal to a point estimate x bar j minus some margin of error, let's call it epsilon j, and then x bar j plus some margin of error, epsilon j, where this epsilon j is going to be approximated to be equal to a t-critical value with some alpha j divided by 2 distributed in each of its tails times the standard deviation divided by the square root of the sample size for that particular sample. Now, since we're collecting a multivariate sample, N1, N2, all the way down to Nk should be the same. So technically we should be writing n for this particular statement, but later on we're going to see when we do multiple samples, we don't need those samples to be the same size. But since we're collecting one multivariate sample, these should all be the same exact number of sizes, else you have to make it that way. So, in particular, we're going to be asking a bunch of people k different questions. That's the multivariate question, or the multivariate perspective. And if we aren't able to get k answers from everyone, then we're only going to consider the n individuals that gave us k responses for our questions, right? And obviously this is going to be the standard deviation for that feature of focus, and this alpha j is going to be the alpha value for that particular feature. So if we sort of zoom out of what we're looking at here, so let's assume that our null hypothesis is that mu1, mu2 is equal to, for example, mu1, 0 and mu2, 0. This could be, for example, age, and this could be, for example, height. So some people believe that the average age for a population is equal to 32, and some people may claim that the average height of the population is 165 centimeters. So if that is the case, that means we need to sample, say, 60 individuals, ask them how old you are, how tall you are, and we're going to get a bunch of bivariate responses from each of our n individuals. So we're going to have a standard deviations for our sample ages. We're going to have a standard deviation for our heights. That's this S1 and S2. We're going to have an alpha 1 associated to testing mu1. We're going to have an alpha 2 for our testing our mu2. And therefore, we're going to have these confidence intervals. For example, if we just have 2, for example, x bar 1 and x bar 2 are sample average age and sample average height for our samples, but we of course can sample k different features and extend this all the way out to x bar k. So since we're assuming that we're going to be working with two-tailed alternatives with the classical two-tailed test statistic, we're going to have our rejection region located in each of these tails. Now, under the current structure, we are allowing our alphas to be different because we might be more confident for testing age rather than height based upon our prior knowledges and prior observations or possibly prior other tests. So for example, in each of these tails, we're going to have, for example, alpha 1 divided by 2, alpha 1 divided by 2 in the two tails of the distribution for x bar 1. We're going to have alpha 2 divided by 2 and alpha 2 divided by 2 for the distribution for x2. And we're going to have alpha k divided by 2 and alpha k divided by 2 in the two tails of the x bar k distribution. And obviously in these two pictures, we're going to have, for example, x bar 1 minus epsilon 1, x bar 2 plus epsilon 1, or x bar 1 plus epsilon 1. And then we have x bar 2 minus epsilon 2, x bar 2 plus epsilon 2, all the way down to x bar k minus epsilon k, and x bar k plus epsilon k, and that's going to give us our confidence intervals, or classical confidence intervals, for each of these claims. Now remember, our null hypothesis that the mean vector mu is equal to this claim mean vector mu 0. So how will we reject? So we will reject the null hypothesis if at least one of these claims, let's call it mu j0, does not belong to our associated confidence interval under some level of confidence C%, and that obviously can change for each of these mu j's. So for example, we could have, for example, our mu10 located there. We could have our mu20 located there. So obviously, if you're within your bounds of your confidence intervals, you will not be rejecting the null hypothesis, in particular those individual null hypotheses. But if you have at least one of these points outside of that confidence interval, so here we would have mu k 0 does not lie within the bounds of x bar k plus or minus epsilon k, that means the element of that vector doesn't match the claimed value of that vector, or they're significantly different from each other, and two vectors can only be equal if and only if every single one of its elements are equal to each other, which means the claimed values of our mu j's must be approximately equal to every single one of our x bar j's, and if we see that at least one of them are very far, that means the vectors themselves are also very far from each other. As we see with the element-wise classical approach for mean vector hypothesis testing, we see that if obviously as the number of features gets really big, one rejection for those null hypotheses will break the entire thing. Therefore, we need to introduce another concept to handle this issue. So to start, we defined family-wide error rate, or the family-wise error rate, as the probability of making at least one type 1 error across our family of hypothesis tests. So, if that is the case, we can write this as a probability statement, as the family-wide error rate is the probability of making a type 1 error for our first confidence interval, a type 1 error for our second null hypothesis, all the way out to a type 1 error for our last. And technically we can represent this as unions as well, so we can write it as T11 union, T12 union, all the way down to T1k. So one thing that we know, at least from the Bonferroni inequality, from probability theory, is that this is going to be less than or equal to the sum from j is equal to 1 to k of the probability of type 1 error for each of those individual elements. So comparing these two inequalities, we can find that the family-wide alpha value is always going to be less than or equal to 1 minus the product from j is equal to 1 to m of 1 minus alpha j. Right? So we can't exactly get the family-wide error rate from this inequality, but what we can get is an upper bound for this probability. So if we have an upper bound, we can actually just choose our family-wide error rate to be the upper bound of this inequality. Because if we choose our alpha FW to be the upper bound, the true value will be less than we're actually saying it is, right? Keep in mind, every time we're working with an alpha value, if we choose it to be a larger value, we're typically minimizing the type 2 error associated with that. So choosing a larger alpha value is not necessarily a bad thing, but your p-values are typically going to be a lot larger than they typically would, and your confidence intervals will also be a little bit wider than they typically would. So let's take as a just quick numerical example. Let's assume that we're working with two multivariate features, and let's assume that we have a multivariate alpha vector, in particular alpha 1 and alpha 2, equal to 7% for the first feature and 5% for the second feature. So obviously if you work with your classical two-tailed approach, you would have alpha 1 over 2 and alpha 1 over 2 in each of those left and right hand tails. And for the other one, so this is k is equal to 1 and k is equal to 2, we would have alpha 2 over 2 and alpha 2 over 2 in the left and right hand tails for that second distribution. So what we're going to do is we're going to inflate that alpha value and do a more conservative hypothesis test. So we know that the family-wide alpha value is going to be less than or equal to 1 minus the product of 1 minus alpha 1 and 1 minus alpha 2, which in this case is going to be equal to 1 minus 0.93 and 0.95, right? So in some sense, this value is what we call the family-wide confidence value, right? So alpha family-wide is going to be less than or equal to an estimate for the family-wide confidence value, and we can find that that's going to be equal to 0.1165, which is higher than both of them combined, right? So when we divide that by 2, we're going to have 0.05825, and that's going to be distributed in every single one of these four tails, right? So instead of doing alpha 1 over 2 in the left and right of the first and alpha 2 over 2 in the left and right of the second, we're going to be doing alpha family-wide upper bound divided by 4 in each of the four tails. Right? So if we want to generalize this to the generalized multivariate case, and we're just going to call this strategy 2, so strategy 2, to follow up from our element-wise classical approach. So what we're going to do is we're going to do element-wise comparisons with what is called a Bonferroni multiplier. So how this goes is we have our k confidence intervals, each of them with their two tails, let's assume. Before we had our alpha j over 2's in each of the tails for each of these k distributions. So let's assume we have that x is associated to rk. And of course, let's assume that mu j is not equal to mu j0, so two tails for a. So then that means we have 2k tails to distribute our family-wide alpha over, right? So we're going to take this family-wide alpha and we're going to split it here, 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 and here in any of the tails. So we have two tails here, two tails here, two tails here, therefore we have 2k tails across all of them. So when we build our Bonferroni confidence intervals, which we'll just denote as Ci mu j Cj percent, actually I don't need to call it Cj percent because we're going to be pooling these confidence togethers. Let's just do a superscript value of b there. So this is going to be equal to x bar j minus epsilon j and x bar j plus epsilon j, where our epsilon j is going to be given by our t critical value associated to some level of alpha in the tails times our typical standard error sj divided by the square root of m. So keep in mind, since we're pulling our alphas together into what we call a family-wide alpha value, and since we have two k-tails to distribute that alpha over, we're going to be distributing our alpha fw divided by 2k in each of those tails. So for each of our tails, obviously we're going to have a t critical value, and the alpha in that particular location is that alpha fw divided by 2k. And we call this a Bonferroni confidence interval, or confidence interval with a Bonferroni multiplier, where the Bonferroni multiplier is this particular object here. And keep in mind that this is the same for all confidence intervals, right? So that's actually very, very useful. So up to this point, we have two variations of confidence intervals for testing the equality or the value of a mean vector. We have the element-wise confidence intervals, which allow for different alpha j's for each feature. Then we have the element-wise confidence intervals with the Bonferroni multiplier, where we take all of our alphas for each feature, we pull them together in some sense, and construct what is called a Bonferroni multiplier, which is going to be the sum for each of our k confidence intervals. And now a third strategy that is sometimes used is sort of like a continuation of the Bonferroni multiplier approach, But keep in mind the Bonferroni multipliers only focus on the alpha values. It doesn't really take into account that we're assuming that our x1, x2 down to xk are all normally distributed, in addition to the vector being a multivariate normal random vector, right? So the third strategy that you can take is what is called a simultaneous multiplier with, of course, a family-wide level of alpha. So what this does is it sort of takes our t critical values, squares them, and tries to map them to an F distribution. So remember, we're going to have k of each of these CIs, where we have, for example, x bar j with an area in each of these tails of alpha fw divided by 2k because we have 2k of them. But when we consider the t squared distribution, which we know is going to be associated to an F distribution, then we know that our distribution is going to be looking like something like this. That is, our two tails are going to be merged into a one right-tailed distribution because we know that these values are going to be mapped in this realm, right? So now this is going to be associated to an alpha FW divided by K level, and this is going to be associated to an F distribution. So this is what motivates the idea of a simultaneous multiplier. So what we're in a sense doing is we're mapping our squared t critical value, which pretty much has an alpha over 2. Actually, let's not square it quite yet. I think a safer way to write it is our t critical value with our family wide over 2k, and we're going to be squaring that. That's going to be mapped to an F distribution, an F critical value, with alpha fw divided by k, alphas in each of those k tails, right? So we have two k tails. Now we're going to be working with just k tails for each of our k distributions, and obviously this needs to be normalized, and the normalization factor is going to be k times n minus 1 divided by n minus k. And in some sense, what we have going on here is we have the n-1 degrees of freedom coming from the k, and then we have this k n minus k term, which are going to be associated to the chi-squared degrees of freedoms for which build that particular f critical value. Right. So in terms of degrees of freedom, keep in mind that the degrees of freedom for this t critical value was n-1 for each of them, and the degrees of freedom for this is going to be equal to k m minus k for each of those k confidence intervals. Now, one thing that I want to mention is that some people will actually change this. So note, some will choose this alpha fw over k to just be alpha over w. Now, keep in mind we still will have k confidence intervals, and choosing alpha fw, which is obviously bigger than alpha fw over k, will be a bigger alpha value, which in some sense is a little bit more safer, but some will say that this would be over conservative or too conservative of a hypothesis test, because we're already pulling our alphas into our alpha family wide. The reason we divide by k is because we have k confidence intervals compared to the 2k tails that we had before. So treating them all with the same alpha is sometimes viewed as over-conservative. Obviously, your p-values will be even larger than they would if you do your alpha fw over k, but as a minimum rule of thumb, alpha fw over k is a bare minimum that you definitely should be using. Of course, if you want to be super safe, alpha fw of course is more conservative, but it's sort of up to you and your preference and sort of your comfortability with these variables that you're actually testing about. The last strategy that we want to introduce is actually the more classical and in some sense most appropriate version for multivariate hypothesis testing, and hence why it's going to be called the multivariate approach. So like we did for the element-wise comparison test, if we have k features, we're going to have k confidence intervals, two-tailed for t, one-tailed for f. But with the multivariate approach, what we're going to have is we're going to have one test, in some sense, one confidence interval for the whole mu vector, right? And that's why we call it a multivariate approach, because it's going to be, in some sense, a vectorized approach. So let's just review what we're working with here. So we have mu is equal to mu0, where mu and mu0 are both vectors, and let's assume that we're working with the two-tailed alternative, that mu is not equal to that mu0 vector. And let's assume that x is going to be a multivariate vector belonging to Rk with k features. In particular, x is going to be of the form x1, x2, down to xk. Let's assume that we already know that the variance of that random vector x is going to be equal to the covariant matrix sigma. Obviously, if you're working with a sampled version, then we know that the expected value of the sample covariance matrix will be equal to the theoretical covariance matrix, sort of like the relationship between sigma squared and s squared. So how would we do this multivariate approach, and sort of how would that look like from the gathering perspective? So the first thing that we need to do is gather a multivariate. Some people will say a k-variate sample of size n. So we're going to be asking n individuals, k questions, right? So n is the number of people you ask, k is the number of features that you're asking each of them. And hence we call it a multivariate sample. So it's still one sample, but it's a sample with multiple questions in it. So for each feature, j is equal to 1, 2, down to k, we're going to have an average for each feature. So in particular, the sum from I is equal to 1 to n of xij, right? So what is xij? So it's the ith response for the jth feature, right? So you ask a bunch of people what their age are, you average their age. You ask a bunch of people what their heights are, you average their heights. So once you have each of these averages, then we're going to have a vector x bar, which is going to be x bar 1, x bar 2, all the way down to x bar k. So once we have that x bar vector, now we can build our test statistic. So our test statistic, which we're just going to be abbreviating by t squared stat, and some people also call this the Hautelling t squared test statistic, which is associated to a t squared distribution. Some people will also call it a Hautelling t squared distribution. This is just going to be equal to our sample mean vector x bar minus the claimed vector mu0 transpose times the population covariance matrix, if you happen to know it, divided by n, invert that matrix, and then x bar minus mu0. And we have already been through where this formula is actually motivated from. Now, one can show that as the sample size, if the sample size is sufficiently large, then this distribution is going to be associated to a chi-squared k distribution, where k again is the number of features, and the alpha value that you would use for calculating p-values or critical values would obviously be your family-wide alpha value divided by 1, because we have one confidence interval or one test or one distribution for all of them at once. Keep in mind, this is not a number, that is a vector. So we have one vector for all k features. Now, usually we do not know the population covariance matrix, so we obviously typically would estimate sigma with our sample covariance matrix, sigma hat. So when you are using sigma hat, the distribution of this test statistic will not typically follow a chi-squared k distribution unless your sample size is really, really, really large. But even then, it doesn't really account for the variation associated to that that sample covariance matrix. So a better alternative, obviously, would be like an F-stat that we sort of worked with our simultaneous confidence intervals. And the structure for that test statistic is going to be the following. So this is going to be equal to, as before, n minus k times n minus 1 multiplied by that associated t squared test statistic. And this is going to be, again, associated to an f, k, m minus k distribution with the same alpha family y divided by 1 alpha in the right-hand tail. So, obviously, if you get a test statistic that is significantly large, so if our f test statistic is significantly greater than 0, or moreover, if it's bigger than our f critical value associated to that alpha family wide over 1 distribution, then we will reject the null hypothesis that the mu vector is equal to that claim vector of mu 0, which means that we have evidence to believe that the vector mu is something else. And you can always collect another sample and retest it if you aren't sure that this is actually the right decision, but that's obviously the downsides of hypothesis testing and one sample test. So those are the basics of one vector hypothesis testing. In the next video, we'll take a look at how to do multiple vectors in multivariate world comparison tests, which would be like the multivariate extension of like the pair difference t-test, pooled difference t-test, and unpooled variance t-test. But instead of two numbers, now we're going to have two vectors. So I hope to see you in that video. Take care.